because it's a hike that I really love. And what's even better is it's in Arkansas. Okay. So this is one you could go do. And since we've been getting all this rain, you should go do it because it's got a beautiful waterfall. This is Hemden Hollow. Anybody heard of Hemden Hollow before? Anybody been to Hemden Hollow? So if you go to the Buffalo River area, Ponca area, Hemden Hollow is around that area. So there's actually two ways to access this hike. There's a place called, if you Google the Compton Trail Head, you can park your car there and hike this trail that way. That's the hard way. Okay. So if you don't mind a strenuous hike, do this one. But you can also access this another way, but you have to float the river. So if you're going to go on a float and you want to take a fun little hike, like park your canoe or kayak with your friends and then hike this part, you have to float the river from Steel, where do you put in Steel Creek to Kyle's Landing. Okay, if you float this segment of the river, there's a part where you can park your canoe and you can go hike. It's very flat, just a kind of an in and out to the waterfall and back to the river. This hike, and you still see the same thing, so it's a lot of fun. But the Compton one, this one's hard. It's down all the way there. You get to the waterfall, hang out, eat your lunch or whatever, hike up. It's literally up the whole way back. So, anyways, really, really fun one though. If you go in a dry season, you'll probably be pretty disappointed with the waterfall, but still a fun hike. Another hike is the Lost Valley Trail. So I'm showing you two today because this is a really great trail. So I actually don't have a picture of the trail here. I have a picture of a cave at the end of the trail. And this is within the cave. There's my husband. Within the trail or at the end of the trail, within the cave, there's a waterfall in this cave. So you have to hike back away. So if you are any kind of claustrophobic or don't go here. But if you don't mind caves and small, tight, dark spaces, bring a headlamp. You'll need a headlamp. And I don't just mean your cell phone. You're going to want something because you're going to need your hands to like crawl through the cave. But then there's a big waterfall within the cave. It's really awesome. So Lost Valley Trail is another good one. All right, that's my two hikes for the day. Please go do them. They're so much fun. All right, acids and bases. Okay, we're gonna talk about a lot here. The where we're headed with all of this, the big components of chapter 10 are going to be next week, Tuesday and Thursday. All right, so this is kind of setting us up today. Is going to set the scene, understanding some foundational things about acids and bases, so that when we get to pH and when we get to buffers next week, you guys will be ready to go with that. In the chat, have you ever hiked Seven Hollows? No. Is that a good one? Should I do that? I wrote this down from the first section, Devil's Holler. Devil's Holler. Is that the same thing? Seven Hollows? It kind of sounds the same. I'm going to write down 7.
I've never been. It's at Petit Jean. It's at Petit Jean. I've never been before, but I'm going on Tuesday morning with one of my friends, so I'll make sure to let you know if it's.
Yeah. Somebody I know just hiked Seven Hollows. I was like, I know really? I've heard this. Okay. Yeah, I can't remember who told me about that. That sounds like a good one. I love Petit Jean, and it's not too far, so.
Yeah.
Well, cool. All right. I'll have to hike that. Okay, but acids, so obviously there's different kinds of acids. We are not talking about recreational acids, everyone. We're talking about, we'll be talking about like citric, obviously. Citric acid is something you may think of when you hear the word acids. Lactic acid, okay. Carbonic acid, these are all important. Hydrochloric acid, that's important biologically, right? Then there's acids that we can use in laboratory. How many of you think of like Breaking Bad and like different crime shows where they drown people in acids? Terrible. It's our entertainment. So anyways, there's all different kinds of acids, but we're going to be talking about and defining acid-base reactions and how acids and bases behave. Now, we've actually already introduced acid-base reactions. You guys remember all the way back to chapter 5 when we were classifying reactions and we said acid-base reaction is a kind of chemical reaction and water's the product. And if it produces water, then you know it's acid-base. Well, that's not necessarily wrong, but it's not the whole truth, okay? So we're going to redefine an acid-base reaction today. But first, what is an acid? It is just a chemical that donates H plus, so a hydrogen ion. I'm going to rewrite that because that doesn't look like an H. Okay, H plus to another chemical. That's what an acid does. So because of that, sometimes we'll call H plus, I'll use the word proton. I'll say it donates a proton. Why am I saying that? Think about hydrogen. I'm going to draw a picture of hydrogen. You've got the nucleus. I'm actually going to draw a plus charge. There's our nucleus, right? It's one proton, protons plus charge. And then you got this electron cloud, okay? But a hydrogen ion has given up its electron. So literally all we have is a proton. That's why we call it a proton, okay? Because that's all it is. So because of that, we nickname acids proton donors. Proton donors. So that's what an acid is. Let's look at an example of an acid. We got HCl in this picture, and then you have these kind of electromagnetic maps just showing you, like, obviously the different electronegativity. So we got the partial positive on the hydrogen, partial negative on the chlorine, right? And the blue regions are the partial positive regions, red, partial negative. In aqueous, I'm going to fill this in aqueous solutions. Why am I saying aqueous solutions? Well, pretty much all acid-base reactions involve aqueous solutions. Okay, water is present to some degree. And when you have water present, what's going to happen is the hydrogen ion is going to be donated to water, to H2O. What's that going to create? Look at the product side. When water accepts a hydrogen ion, what do you get? You get this thing in the brackets. Anybody remember the name of this? You should actually recognize this. What is this called?
Butane.
Somebody said something. It's a polyatomic. And we're like, oh yeah, polyatomics. I don't remember those. Polyatomic. What polyatomic is this? Obviously, it's H3O trioxide. Not quite, Keegan. That's not a bad guess. This is even closer, Tyler. Not hydroxide. It's hydronium. Hydronium. Okay, H3O plus. So the acid obviously is the HCl. It's donating its hydrogen or losing its hydrogen to water. Okay. And what you make is H3O plus. But I want to read this portion of the sentence. But H3O plus and H plus are used interchangeably. Why? Well, that'll make more sense when we get to pH. Okay. We measure the acidity or the basicity of solutions according to pH. And when we're calculating pH, we are actually measuring the concentration of these things. Concentration. So these are synonymous, okay? Sometimes I might say, what's the concentration of H3O plus? Sometimes I might say H plus. They're synonymous, okay? Interchangeably. This hydrogen is attached to this oxygen here in water, but it's not held very tightly. Like it can come on and off and on and off. So that's why we say these are used interchangeably. All right, I know this probably might be a little confusing right now, but as you get more familiar with acids and bases, I think that'll be understandable. So to continue with what we're thinking about, again, what happens when we dissolve an acid in water? Well, we just looked at HCl with water. Okay, what happened? The HCl gave up its hydrogen, water accepted it. So the same thing's going to happen here. We got a different acid and we got water. Can you write the products this time? We got HNO3. This is going to be your acid. So if it gives up, if it loses this hydrogen, remember that's what acids do, they donate H plus. It's going to give it to what? To who? To water. What are you going to make? Anybody tell me one product? Similar to what we just made. Tyler said it, hydronium. And yep, Keegan said it, nitrate. So you're going to get H3O plus and NO3. Is that right? Just NO3? It's got to have a minus on it. Okay, it's NO3 minus. Why? The charges have to add up on both sides. I got two things that are neutral, no charge here. So everything has to add up on the product side. I got a plus, that's not balanced with neutral, but a plus and a minus balance to neutral. That makes sense what I just said? Plus, think about this. If you got H plus and NO3 minus joined together, when you lose the H plus, what you have left over is the NO3 minus. Okay, you can't forget the minus. All right, so what you see happens is that the H plus attaches to the, what part on water actually is it attaching to? It's the oxygen. And that makes H3O plus, okay? But what part of the oxygen? I want to scroll back up to the previous slide real quick. Look at that oxygen. Over here, we had oxygen with two lone pairs. One of those lone pairs accepted the hydrogen and forms this bond, this dash, okay? So this right here, it was a lone pair on the oxygen. Now those electrons are in a bond. Okay, so this is those two electrons that were the lone pair on oxygen. Every bond is composed of two electrons. I want to point out something. Hydrogen ion is just a proton. It has no electrons to donate to the bond. Both electrons, when something accepts a hydrogen here, here's the water, this is the base. In other words, we're going to define a base in just a minute, but it has to supply both electrons when it accepts the hydrogen, okay? It has to supply both electrons for that bond, because the hydrogen ion has nothing to donate to the bond. All right, but thinking back about this reaction again, the nitric acid and water, we could also omit water and convey the same thing by writing the reaction for the dissociation of HNO3. Dissociation, what does that mean? The acid disassociating or dissolving into its ions, okay? So if we just take water out of the equation, sometimes you'll see people write the dissociation of this acid would produce what? All you're doing is you're saying, well, it's going to make H plus and NO3 minus. Same things, you're just omitting the water. And we would just, because we're not viewing the water for kind of clarity, we just call it the dissociation of HNO3. All right, that's a dissociation reaction. Okay, questions so far on what an acid is, what an acid does? All right, so we've just looked right now so far at the transfer of one hydrogen. All right. Many polyatomic ions can exist as acids, and we actually just saw that with HNO3 because nitrate, that's a polyatomic. Throw a hydrogen on there, and now it's nitric acid. Other examples are down here below, but several can donate multiple protons. So some acids can only donate one hydrogen. We saw that as an example with HCl and nitric acid, HNO3. Other acids can donate multiple hydrogens. So we have different name for these, different names. Hydrochloric acid, we call this a monoprotic acid. Any acidic hydrogen, anything that could be donated is highlighted in red. So you just see one red hydrogen there. That's the one that could be donated. That's the one that makes HCl an acid. All right, on HNO3, again, you just have one hydrogen, so we also call that monoprotic. But look at sulfuric and phosphoric acid. Sulfate is the base polyatomic ion here. And when you have hydrogens bonded to those oxygens, now you have sulfuric acid. And we call it a diprotic acid because both of those hydrogens could be donated. Phosphoric acid, the base polyatomic is PO4 minus 3. And when it's fully protonated, you have a triprotic acid. You see those 3 red hydrogens. So we got monoprotic, diprotic, triprotic. And these are all, I want to make a point, these are all inorganic acids. Okay, what do I mean when I say inorganic? I'm sure you've heard that word before, but what does that actually mean? Inorganic as composed or compared to organic. You guys know it does not have carbon in it, okay? No carbon. Organic means it has carbon in it. So these are all inorganic acids where we use the mono, di, triprotic. Okay, but I want to pay attention to this last thing down here. Even though you have some acids that can donate multiple protons, they always and only lose 1 acidic hydrogen at a time, 1 proton at a time. So let's take phosphoric acid, and I want to write out the different steps showing it losing 1 hydrogen at a time. So here's what I mean. You got H3PO4 starting out. This is the fully protonated triprotic acid. So we're just going to write the first dissociation reaction. All right. So the first step, the first dissociation would produce 1 hydrogen, 1 at a time. But what's left over? What's going to be left after this loses 1 hydrogen, our initial reactant? All right. Bailey said H2PO4. I like that. What's the charge? Is it still neutral? If you give away something with a positive charge, you yourself are changed. Yep, -1. Okay. Let's write the second dissociation. So it's lost 1, now it's going to lose another 1. So again, we're going to create an H+, and it doesn't matter if I'm writing the H+ or the other thing first. I just know I'm going to get an H+, so I'm just going to go ahead and write that. So now what's my other thing? Once this loses a hydrogen, what's left over? What do y'all think? H2PO4. Is it neutral? Tyler gets it -2 charge. You gave away another positive, so you go down in charge again. All right. Okay, and then you could even draw it for the third dissociation. But anyways, it's 1 at a time. One thing I want to point out, I'm going to put a box around these really quick. These compounds, these molecules are unique, okay? Why? There's something, I'm going to introduce this word later too, or come back to this word later, but I'm going to introduce it now. They're called amphiprotic. AMPHI, amphiprotic. It's kind of a weird word. It's like amphibian, but not amphiprotic. What does this mean? Anybody heard this word before? Amphiprotic? Amphiprotic is a word that means it's a molecule that could be either an acid or a base. Okay, here we've shown it donating hydrogens, giving hydrogens away. So we've shown the dissociation step, they're acting like acids. But this could go back the other way. It could accept a hydrogen and remake your initial product. In that case, it's acting like a base. So something that is amphiprotic can act like an acid or a base. It could do both. It has a hydrogen still on it, so it could give away another hydrogen, or it could accept a hydrogen. It could be an acid or a base. And I know we haven't even defined what a base is yet, but that's what a base does. It accepts a hydrogen, the opposite of an acid. All right. So it can act like an acid or a base. It could give away a hydrogen or receive one. All right. So I'm just going to put a little star there. It's kind of a vocabulary word to remember. All right. Let's keep going. I know a lot of this is just kind of the terminology and getting used to the concept of an acid. So we're going to work some problems in a minute. If an acid has multiple hydrogens, how do you identify an acidic hydrogen? So that indicates that sometimes you have hydrogens on molecules that cannot be given away. There's only certain ones that can be given away. Only those for inorganic acids. We already talked about what inorganic means. Inorganic, it's only those bound to electronegative atoms, oxygens, fluorines, chlorines, where you're going to get a semi-positive hydrogen, a positively polarized hydrogen. Okay, so we looked at several examples up on that slide that had the monoprotic, diprotic, triprotic. Go back and look, and you can see all those hydrogens are bonded to like a chlorine or an oxygen or nitrogen, very electronegative elements. But so this is for that's for defining inorganic acids. How do you identify acidic hydrogens on inorganic acids? For organic acids, would that mean they have dipoles? Yes, Bailey. That's exactly what that would mean. In organic chemistry, acidic hydrogen are usually bound to or found in a certain group. It's called a functional group, if you've heard of that term before. I'm going to write the functional group here, COOH, okay? There's a name for this. We're going to get to that in chapter 12. Hopefully we'll have time to do that. These are called carboxylic acids. That's the name for them. And what a carboxylic acid is, it's a functional group. Okay, that is chapter 12. We will get to functional groups. This is just one, okay? So literally this group right here, anytime you see a COOH, and that may not be the entire molecule, just a portion of the molecule. So I'm going to give you 3 real examples. Anytime you have a hydrogen within a COOH, that is your acidic hydrogen. And notice carbon is present. So that's why it's organic. Okay, let's consider acetic acid. We've used acetic acid a lot in this class. I looked at lots of examples where you have acetic acid in your reaction. You draw the Lewis structure out. Obviously, we have COOH right here. This is what acetic acid looks like. This is what the Lewis structure of a carboxylic acid looks like. Okay, it's this portion right here. So guess what? All these hydrogens on the carbon, not acidic, not acidic, not acidic. Those are not going to be donated, not going to be given away. Okay, now as far as why this is the way it is, involves a whole other branch of chemistry called resonance, and you talk about charge burdens and all this stuff that I'm sure you guys probably don't want to get into right now. So unless you dive a whole lot deeper into chemistry, it's hard to understand why this is the way it is. So you just kind of have to take me at face value. This right here, this hydrogen right here, this is the only acidic hydrogen. It's part of the carboxylic acid. And it's obviously, you can see, I'm gonna draw this on here. It's positively polarized because it's bonded to a very electronegative atom, oxygen. So it's easier for it to be donated away. All right, lactic acid. Why is lactic acid important? My husband loves to come home from the gym and tell me how sore he is the next day. Right, guys? Because you just lifted so many weights in the gym and you're so sore and your muscles. I'm just kidding. I know not all guys are like that. I mean, I'm very proud of him for going to the gym. I wish I went to the gym as much as him. Lactic acid. That's what you feel when your muscles are sore, right? Lactic acid is produced as you work out. Causes us to feel kind of sore. CH3CH. And we got this OH group down here. And look, there's I'm going to do it in blue to keep with my color coding. There's our carboxylic acid. Okay. So what that means is that this hydrogen right here is the one that's acidic, positively polarized. This is what makes lactic acid acidic. Now, if you go to Google and you say, how many acidic acids does lactic acid have? It's going to tell you 1 to 2. Okay, 1 to 2. So sometimes, because we also have this hydrogen right here bonded to an oxygen, sometimes that one can be acidic as well. But the main, excuse me, the main acidic hydrogen is the one in the carboxylic acid. All right, sometimes this hydrogen is acidic. Okay, but again, not these hydrogens, not those, not acidic. All right, last example, citric acid. We get that in our diets. I love summertime. I remember last summer opening my fridge and I was like, I had like 6 or 7 different kinds of fruit in my fridge. I had like cantaloupe and watermelon and like blueberries and strawberries. And I was like, this is getting out of hand, but we love fruit at our house. So give me all the citric acid. Sometimes my daughter, she's 2.5, actually almost 3. She literally just loves to suck on a piece of lime or lemon. I don't know how she does it, but she'll ask me. I love to put like lime or something in like a club soda, and she'll just want to suck on it. I cannot. My mouth is watering right now, just like thinking about that. But here's citric acid, the Lewis structure. So it looks a little bit different. You don't see the carbons. Okay, but do you guys remember, have we talked about these kinds of structures before in this class at all when we did Lewis structures? I don't remember if we did. This is just a little bit of a different representation. Okay, the carbons here have to be understood. They're there, but they're not drawn in with a C. So anywhere 2 or more lines come together. So here, anywhere there's like a joint where 2 or more lines come together, there's a carbon. Okay, or if you had like a dead end. So if you had something that looked like this, there would be a carbon right there, a carbon there, and a carbon there. All right. So that's how these structures work. So I'm going to draw in all the carbons. Carbon there, carbon there. Don't worry, I'm not going to have you draw something like this, but I just want you to identify where are your carboxylic acids. How many do we have on this molecule in citric acid? Six, 4, 3. Okay, I agree with Keegan. There's 3. Okay, there's 1. You see how that's a COOH? Here's another one. Another COOH. Yep, Keyshawn said it too. So we got, here's another COH. So we got 3 carboxylic acids. Okay. So what that means is these hydrogens, I wrote over it. I'm just going to underline them. These hydrogens right here, these are the ones that are acidic. There are understood hydrogens that we're not seeing in this. So this carbon right here, this carbon would have a hydrogen bonded and a hydrogen bonded because every carbon's got to have 4 bonds, right? So on these types of structures, we don't draw in the carbons and the hydrogens. If the hydrogens are bonded to carbon, we just draw all the little lines. But none of these hydrogens on any of these carbons would be acidic, okay? They're there, but they're not acidic. What about this hydrogen? It is bonded to oxygen, but if, again, this is where chemistry is nuanced, and this is what makes it so challenging. There's not like you can't generalize and say, oh, anytime a hydrogen is bonded to oxygen, it's always acidic. Because if you actually Google citric acid, this is not an acidic hydrogen, even though it's bonded to an oxygen. Okay, and then there's difficult reasons for why that is. But I just wanted to give you 3 examples of organic acids, acetic, lactic, citric acid, so that you could practice identifying the carboxylic acid and the acidic hydrogens. Okay, questions on what we've gone over so far? We've kind of spent a good amount on that. All right, we're going to pause our definition for acids and we're going to move to bases for a second. So when an acid gives a hydrogen away, another chemical component receives that hydrogen. Okay, So it has to donate to something, and that's the base. So the base accepts the H plus from the acid. So we nickname bases, if acids are proton donors, bases are called proton acceptors. Whoop. So thinking about the reactions we saw earlier, we saw something like this. HCl plus H2O makes H3O plus and Cl minus, all right? That's what we saw earlier. We looked at nitric acid as well. Water is the base. Water is accepting the hydrogen from HCl. We don't think of water as a base, but it can act like a base depending on what it's around, okay? Everybody has one of those friends that, depending on who they're around, exhibits different behavior. It's not you, right? So water's that way. Depending on who it's around, it can act like an acid or it can act like a base. But what's actually happening? What is H plus likely to attach to on the base? So remember, I zoomed in on the hydronium ion and we looked at that bond earlier. It's attaching to lone pairs, okay, which is on the oxygen for water. But for any base, it doesn't have to be oxygen, but there's got to be a lone pair present. Okay, because again, an H plus has no electrons to donate. Every chemical bond is made up of electrons. H plus has no electrons. So that both electrons for the bond have to come from the base. So you cannot be a base if you don't have a lone pair available, because then you have nothing for the hydrogen to bond to. All right. So two very common bases, two very strong base. Well, one of them is a really strong base. OH minus. What is the name for OH minus? Do you guys remember? This is another polyatomic. Thank you, Grayson. Yeah, Summer, Tyler, good. Hydroxide. All right, hydroxide. Now, this could be in many forms. A lot of times you'll see it paired up with like a group 1 or group 2 element. So you'll see it in the form of like NaOH, sodium hydroxide, or lithium hydroxide, or calcium hydroxide. All these are strong bases, okay, because they're all aqueous. So they all just dissociate into their ions and they produce or generate OH minus. That's the base part. The cation here has nothing to do with the actual base part. It's just sometimes these are delivered in compound form. You'll see them in compound form. So how would this accept a hydrogen? Well, let's just show a little reaction. If, say we had sodium hydroxide and then we have like some kind of acid, and that acid is going to give away its H plus. So what's that going to produce? If this is our base, and it's going to accept, because bases are proton acceptors, and it's the lone pairs on the oxygen is going to grab up that hydrogen. What's it going to make? This NaOH is going to dissociate into Na plus and OH minus. So we'll have Na plus floating around in solution. And then what else? Yes, Kendall. Okay, H2O. So you guys remember in chapter 5 why we said these are called acid-base neutralization reactions? Because look what you're making, something very neutral, a neutral product. Now you don't always make water, but acids and bases do neutralize each other. The compound is neutral, okay? Or I should say more neutral. All right, what's the other one then? NH3. What's the name for this? NH3. We've written this molecule several times. Close, Summer. That's the acid form of this. Ammonia, there we go. Not ammonium, but ammonia. And where's the lone pair? Well, I'm going to zoom in for just a second. There it is. So we got a lone pair, good. We can accept a hydrogen. So how does this accept a hydrogen? I'm actually going to scroll down to the next slide because I just remember these reactions are literally on the next slide. So here's, look, I'm going to keep that visible, but look, here's ammonia down here. If we have some sort of acid, A stands for acid, and then that's just showing you the acidic hydrogen. That lone pair is going to grab that hydrogen, and what you make then is the ammonium ion, NH4+. Okay, and then what's left over from the acid is the A, the rest of the acid molecule. Okay, now I want to point out something important here. Things don't just trade hydrogens. They also are changing what the charge is. Okay, if you're giving something positive away or you're receiving something positive, your charge is also changing in the process, and we can't forget that. That seems not significant, but it is significant. Okay, so we have NH3. Starting out, it's neutral. NH3, no charge. Okay, and when you add a hydrogen to it, it becomes NH4 with a plus charge. Okay, it creates a positive charge. Again, that seems not significant, but it is significant. Hydroxide ion, we saw this starts out, it's a negatively charged base. Well, when you add the hydrogen to it, you create neutral water, no charge. So we can actually summarize what I just said, I think, on this next page. Or next slide. Acids lose an H+, which is technically a positive charge. So they decrease in charge. They go down by 1. For every hydrogen they lose, they go down by 1 in their charge. So 2 examples. If you're neutral starting out, you're going to become negatively charged, okay? HCl. That's an acid, a really strong one. When you lose the hydrogen, so this is neutral, no charge starting out, you become Cl-. Okay, -1. And then you have the H+ too. Okay, if you are a -1, you become a -2. So we looked at an example of that actually already. We had H2 when we were talking about phosphoric acid with a minus charge, and we were drawing out all the dissociation steps earlier, talking about triprotic acids. Okay, if that loses a hydrogen, what you have left is HPO4 -2. Decreases by 1 every time you give away a hydrogen. Okay, what about bases? It's the opposite, right? So they're gaining a hydrogen ion, which is a plus charge, so they increase in charge. Neutral bases become +1, bases with a -1 become neutral. So the examples we looked at here were the NH3. When you add the hydrogen ion, you become NH4+. Started out neutral, now you're a +1. Upgrade. If you are OH- and you receive the hydrogen, accept the hydrogen, now you're water and you're neutral. So those are just examples. And I mean, there's so many more, there's endless examples we could write for this. Okay, some of you are like, yeah, I'm on board with this, makes sense. Some of you are like, I'm so lost right now. So if that's you and you're just like, I'm a little confused about acids and bases still, we're about to do some practice, but here's all I want you to know. If you don't get anything that I've said so far, this is the summary. An acid donates H+ and a base accepts it. Okay. Now, you can't just know this sentence. You have to be able to identify this when you're looking at a chemical reaction. But if you know this sentence, you should be able to then identify it. If I give you any reaction, that's an acid-base reaction. Okay, that's the summary of everything we've talked about. Here's just an example picture. Ammonia and HCl. The nitrogen grabs the proton, you form ammonium, and what's left over from the acid is the Cl minus, okay? So, all right, I think I have one more review slide, and then we're gonna do a practice problem. And I got a poll question for you guys. So, am I going too fast? Do I need to go back to any slides? Everybody keeping up so far? Okay. I told you now, maybe a little fast, okay. Can you show the last example right here? Keyshawn? I'm just excited about my poll question, so I'm trying to get to it. Before that slide. Okay. All right. So earlier I mentioned that I had told you that acid-base reactions are any reaction that produces water. And I didn't lie to you, but that's just not the only case. Okay, we just need to expand the definition. So we're going to redefine what an acid-base reaction is, and then we're going to do our practice problem. It is a reaction in which a hydrogen ion is transferred. Okay, so that sounds a little more vague because that encompasses a whole, so many other different kinds of reactions that can be acid-base reactions, but you don't necessarily have water as a product. For example, this one right here is acid-base, but you don't have water as a product, but you still have a hydrogen being donated from the acid to the base. Hydrogen being transferred. Okay. So again, this is all just review pictures. These are all straight out of your textbook, these images. B standing for base, showing you the lone pair, showing you taking the hydrogen from the acid, and then showing the products that you're forming and how they're changing in charge, okay? This base is neutral starting out. Now it has a plus charge. You see the acid is neutral, no charge. Now it decreases to a -1. So these are just summary pictures showing you all the different nuances and little things we've talked about so far. All right, here's the practice problem. I want you to look at these. I'm going to do the first one with you. Identify the acid and the base in each of the following reactions. So we got CH3NH2 and we got water. Now, just looking at, by the way, we're just looking at the reactants, okay? We're not looking at the products yet, but we're going to try to label the acid and the base. That's just going to be on the reactant side. We'll consider what our products are, but we're going to go back to the reactant side and label our acid and base. Looking at these two, I don't know which one's the acid and the base yet. I see that this nitrogen is going to have lone pair. I know oxygen will have 2 lone pairs. So both compounds here could be an acid or it could be a base. So if I'm just looking at the reactants, I don't know. I need to consider what my products are. Then I can go back to the reactant side and label. So I know that in this first compound, it's the first product written as well. You see how they're different? We got CH3NH2. That becomes CH3NH3. And it has a plus charge. But that tells me it gained. So if I were to draw this to this, it gains an H plus. Does that mean it's, Keyshawn, you beat me to it. It says that would be a base. All right, so we're going to label this as the base. Water, okay, right here, it was H2O. It's the second product written. So now it's OH minus. So it lost an H plus. So lost or donated or gave away, whatever. So that makes it the acid. Okay, so you look at the second one, and I'm going to launch my poll question. And when you think you got it, I want you to just tell me which one's the acid, which component is the acid. I'm believing this is going to be the first poll question that we get 100% accuracy on. Don't let me down. No. We didn't get it. I'll show you the results in a minute. No, we definitely didn't get it. All right, I'm gonna give about 10 more seconds. Get them in, get them in. All right, in the poll. I thought we would get it. It's okay. Most of you guys picked HPO4 with a -2 charge, and you said that's the acid. So remember, first off, your acid can only be on the reactant side. Okay, so we consider what our products are, but we are not labeling any of the products as our acid and our base. We're only labeling reactants. Okay, see, that's what we did up here, only on the reactant side. So we should not be labeling either of these things as the acid, okay, because they're on the product side. That already eliminates 2 options. All right, we need to consider what's happening here with the formula and the charges so that we can go back to the reactant side and then label it. All right, so I'm going to erase my scribbles. Question in the chat: are both acid and base always going to be on the reactant side? Yes. Yep, Allie. We will also learn to label the product side, but we have unique names for those. So let's look at OH minus becomes H2O. What happened here? Did it gain or lose an H plus? Gained. I agree. So does that mean it was the proton donor or acceptor? Does that mean it's the acid or the base? That should mean that it is the base. And we identified OH minus as a strong base. Remember, we said, what are 2 strong bases earlier? And we wrote OH minus as the first example of a really strong base. All right, so that must mean this is our acid. So let's look at what's happening. It's HPO4 2 minus, and it becomes PO4 3 minus. So it literally lost the 1 hydrogen it had. So it lost an H plus. So that definitely means it's the proton donor, so we call that the acid, right? Now, again, just because on both of these we have acid written second and the base written first, don't be confused by that. It could be in any order, okay? We don't always write the base first and the acid second. Let's consider, so anyways, that was, the majority picked the right choice, HPO4 with a -2 charge. That was the acid. The reason we cannot label any of the products as the acid is because those are the things that result as a, or I should say, are produced as a result of the hydrogen transfer. Okay, so none of those things are donating a hydrogen. They're what's produced after the hydrogen is donated. All right, we got H3O plus, and that becomes H2CO3. Bradley says, oh, I don't know if this comment was for this one or the previous one. What happened here? Looks like we went from HCO3 to H2CO3. We went from HCO3 to H2. So Kendall and Bradley both say the base. Yep, it gained an H plus. So this is the base. Again, it just so happened on all 3 of these, the base was written first. So by default, this has got to be the acid. But let's look at what's happening. We got water, H2O, becomes OH minus. So it for sure lost an H plus. Okay. So please be prepared on a chapter 10 quiz or on exam 4 to be given a reaction like this on the homework and to identify what the acid and what the base is. questions on this? Grayson, water's not always an acid, right? That's correct. Water can be either. It depends on who water is around, okay? So earlier when we started the lecture, we saw water receiving hydrogen from things like HCl and HNO3. Those are really strong acids. So if water is in the presence of a really strong acid, it plays the role of a base. But if water is in the presence of a base, look at this, number 3, it plays the acid, the role of an acid. So it's kind of like the supporting actor. It lets the lead actor lead, and it just does the opposite role, okay? I know nothing about theater, so I have no idea how supporting actors work. All right. We're going to move on to the last big topic for today, conjugates. Anybody heard the word conjugates before? All right, well, I'm going to introduce like what happens in an acid-base reaction, how we get conjugates before I just define what they are. Hand raise emoji. There we go. When an acid and a base react, the result, so what we're talking about now are the products. The products are a weaker version of acids and bases, right? They are themselves acids and bases, but they're usually weaker, okay? So let's read these two statements. The acid that results from the base is called the conjugate acid of that base. The acid that results from the base is called the conjugate acid of that base. So what that says is the base is going to produce an acid. So let's scroll back up here for a second. The base was HCO3 minus. What it made was H2CO3. This is actually called carbonic acid. This is part of your blood buffer system. Okay, it's just it's a weak acid, all right? So the base will produce, this would be called the conjugate acid. That's what this statement is saying. The acid that results, the acid on the product side, we call it the conjugate acid of the base. Okay, this one, the base that results, so it's on the product side from the acid, is called the conjugate base of that acid. So look at, we're now going to define what we call conjugate acid base pairs. You can pair up one reactant with one product. On the reactant side, you're going to label it as an acid or a base. On the product side, you're going to label it as a conjugate acid or conjugate base, and then it'll be opposite. If it is a base on the reactant side, it will be the conjugate acid on the product side. If it's an acid on the reactant side, it'll be a conjugate base on the product side. So that's what you see here. Base is in blue, acid is in red. So we've got those labeled on the reactant side, and it's got these black lines, kind of like what we drew up here, connecting lines between your conjugate acid base pairs. So we would call this the conjugate base and the conjugate acid. Okay, so why is that? Look at this. We got the base, abbreviated B, could be any compound, but we see it has lone pairs. It's going to pull this hydrogen off the acid. The acid gladly donates it. And what you have is this right here, okay? A compound that now has a hydrogen. So it could turn around and donate that hydrogen to somebody. And if it does that, it could be an acid. Okay, acids give away hydrogen. What's left over is the rest of the formula. Now there's a lone pair on it. Okay, we actually didn't draw that in. I don't know if we necessarily had to, but if it has a lone pair, it can receive a hydrogen. So for example, we had acid as the water, or the water as the acid in number 3 here. If we got OH minus, there's lone pairs all over this OH minus. Okay, so it could now be a base. OH minus is a really strong base. Now I know you're like, but I thought it said it produces weaker acids and bases. Usually, yeah, so I guess I should say result is a usually weaker acid and base. But there are cases when, such as water, water is already a very weak acid or a very weak base. So what it produces here, when it makes OH minus, that's a really strong base. But it usually produces a weaker acid or base. Okay, any questions so far on conjugates? We're going to spend some time writing out conjugate acids and bases, just so we fully understand some of this. Everybody got everything? All right, we're going to do some practice. What is the conjugate base for each of the following acids? So we have these acids, and what do acids do? They donate H plus. So we're going to draw essentially the dissociation reaction for all of these. All right, so what's going to be left over? HClO4, and when you make H plus, what else do you get? I want somebody to tell me. Kendall, ClO4, is it just ClO4? Is it plus or minus? Summer says minus, Bradley says minus. I agree. Remember, acids decrease in charge by 1. Yep, Danielle says negative. Good. Okay, so this would be the conjugate base. I'm actually going to switch my color over to denote a different color. So I'm going to write all the conjugate bases in blue. So we got H2S. If it gives away a hydrogen, what's left over? Summer said HS with a minus. That's right. So if you're neutral starting out, you decrease 1, you got a -1 charge. So that is the conjugate base as well. Okay, now we have pH4 plus. So that gives away a hydrogen. We'll make what? What do y'all think? Danielle said pH3. Should there be a plus or a minus on it? It should be neutral. That's exactly right, neutral. And HCO3 minus. And that gives away a hydrogen. Bailey says CO3. With a plus. Danielle, pH3 is going to be neutral because it was a +1 on this side and it gives away a plus. So now what's left is just neutral. But going back to CO3, yeah, we got a -1 right here. And if you give away a plus charge, now you decrease again. Remember we said acids always decrease by 1. So now it's a -2. Okay, so all these are the all of them are the conjugate bases. Okay, what is the conjugate acid for each of the following bases? So what's happening here is we're saying plus H, plus H, plus H, plus. Now what do we get? We're going to write the conjugate acid. All right, Gliana says HCN for the first one, neutral. I agree. You're going to just add up the charges on this side. So a negative and a positive make neutral. You got SO4. You got a -2 and a +1. So what we should have for the second one would be H. Tyler said HSO4 -1. We got water and H plus. We actually already saw this at the beginning of lecture. We said that makes H3O plus. Got a 0 and a +1. Makes a +1 on the product side. So then lastly, we got bicarb, HCO3 minus. And when you add the hydrogen, you should get H2CO3. And then the negative and the positive make our conjugate acid here neutral. So these are all conjugate acids. So I want you to both be able to write out the conjugate acid or the conjugate base, and then look at a reaction and label the conjugate acid-base pairs. Remember, conjugates are always written on the product side. Acids and bases are always on the reactant side, okay? Last problem. I think this is the last one we're going to do today. Any questions on what we wrote out for this slide? Anybody need me to sit here for a minute? Okay. It says hydrogen sulfide ion is amphiprotic. There's that word again. Okay, why? Well, HSO, not 4, 3. It could accept a hydrogen. Okay, so if it adds a hydrogen, we'll get H2SO3, not a minus, sorry, neutral. Or it could give away a hydrogen. So if it gains, or it could lose a hydrogen. If it loses, what you get is SO, I keep writing 4, 3 with a -2. Okay, that's why it's amphiprotic, just like bicarb. Look, we wrote bicarb gaining a hydrogen. Up here, we wrote bicarb losing a hydrogen. Bicarb is also amphiprotic. All right, so it's amphiprotic A, part A. Write an equation for the reaction of HSO3 minus with water. So I want you to start writing a reaction with HSO3 minus and water as your reactants. Write an equation for the reaction of HSO3 minus with water. That's what you should have so far. In which, let's read the rest of the problem, in which the ion acts as an acid. So I want you to tell me what products we're going to get. Keegan, yes, amphiprotic means it can be an acid or a base. It can give a hydrogen away like an acid, or it can receive one like a base. All right. What products are we going to get here? So we're saying this is the acid, and this is the base. Kendall says we'll get SO3 and H3O, okay? But they can't both be neutral because I see I got a -1 and a neutral on my reactant side, and then I can't have neutrals because that doesn't add up. So Tyler says -2 and +1. What do y'all think about that? Remember, acids decrease by 1. So if you got a -1 on your acid, you should have a -2 on the conjugate base. And if your base is neutral, then it increases by 1. So you should have a +1 on the conjugate acid. Okay. Part B says, again, write an equation for the reaction of, sorry, okay, let me pause. Can you explain where the -2 is from again? I'm going to actually offer that. Does anybody feel like they know the answer to that before I just jump in and affirm or explain? So Allie says, can we explain where is this -2 coming from? Keyshawn says, is it because it lost a hydrogen? Well, yes, it is an acid, so it is a proton donor. So it's going to, water, what it's going to do, so if you like to draw the arrow, you could say this lone pair is going to grab this hydrogen off of that HSO3. So when it loses the hydrogen, because we know this is really the combination of H plus and SO3 minus 2. When those two come together to give us this, it's overall a -1 because of plus and a -2. So we're really just seeing, okay, when we take this away again, what's left over is SO3 minus 2. If you give away, it's giving away something with a positive charge. So if that's happening, then you yourself are decreasing by 1 because you lost a positive charge. Okay, I get it is sometimes kind of conceptually hard to like make sense in your head. But hopefully if on paper you see the charges on this side have to add up to the charges on this side. Then I'm not saying they're going to be the same, but they have to add up to the same total. Does that help, Allie? I don't know if that did a good job or not. A little. Okay. Basically, if you get lost, let me scroll up to the slide that's going to help with what we said on this. Right here. This is the slide you come back to. If you're trying to write out these products and reactants and you forget what the charge is going to be, acids lose a hydrogen, so they decrease in charge. Okay, the conjugate base will always be -1 in charge from the acid. Bases gain a hydrogen ion, so they always increase in charge. So the conjugate acid will always be +1 more compared to the original base. Okay, that's what we see here. Conjugate acid is a +1, base is neutral. Conjugate acid is neutral because the base was a minus. It's increasing as you go from base towards conjugate acid. There we go. Good. All right, last thing. So part B, write an equation for the reaction of the HSO3 minus with water. Now the ion is going to be the base. So we're saying the ion is now going to be the base. Why can we just flip it like this? Well, we said it's amphiprotic. It could be an acid or a base. So we're going to play it out both ways. What would we get? Bradley says H2SO3, and it's going to be neutral. And then if water is the acid, it's going to give away. So this oxygen is going to have lone pairs, right? It's going to grab one of those hydrogens from water, and we'll get OH minus. Okay, so we have a 0 and a -1, and that is the same as 0 and -1 on this side. So the charges all match. Can y'all label the conjugate acid base pairs? If this is your base, this is your conjugate acid. Remember, conjugates are only on the product side. Acids and bases are only on the reactant side. If the water is the acid, then the OH minus is the conjugate base. Kiara, what do you mean by is it always going to be opposite? Like on one side it's the acid, on the other side it's the base part? Yes, you would never have a reaction where it's like A plus B makes C and D. You'll never have like acid and conjugate acid, okay? You'll never have that. The conjugates are always on the product side, and then the acids and the bases are always on the reactant side. And then they flip, yeah. If it's the acid on one side, it's the conjugate base on the other. Can a base have a conjugate base? Nope. The base is always paired with the conjugate acid. Yeah, so yes, they always flip. To answer your original question. They always become the opposite thing, just in conjugate form.